CSC 104 for 100 level computer science students and 228 for 200 level of other science departments. And I'll be glad to repeat that again so that for emphasis, you know where you are. This class is CSC 104 for 100 level computer science students and CSC 228 for students of other departments. Today we are looking at software practice. However, this is going to be the second edition of that category of software practice learning and understanding. The first edition was done some months ago, and that introduced you to basic programming and with emphasis on Visual Basic. Today, we are going to dip it further by looking at the generic Fortran programming, object-oriented Fortran, and the extractions from them. However, you must note from the beginning that our emphases are not only on those programming languages alone, but in the concept that drives the category of those programming languages. Ladies and gentlemen, I am happy to welcome you to this class, and it is my pleasure to take you through the journey of this course. I'll be sharing my slide so that we can actually take it from the basics. I will expect you to take down notes as appropriate, and that will be the right thing to do. So, what are we learning today? We're going to learn the processes involved in this category of programming language. And we are going to look as a block the generational programming language called Fortran, but with emphasis on the subject matter called software practice 2. Going further, there are categories of items, concepts that must be well understood. For first of all, you do understand that programming language is just a form of a language. I'm speaking with you in English. Some of you are from native Yoruba land that speak some other form of Yoruba language. Some of you are of Igbo extractions. You also speak Igbo language. The Hausas will speak Hausa language. You know, the concept of a language is a means of communication, of transferring some set of text, knowledge, idea from one conceptual entity to another conceptual entity. This is just the way it is in the computer framework. You have a programming language as a set of language that translates your industrial and your systematic framework, your model, into an operational output via the use of a computer. So what is in the central part of the whole transformation is the word computer. So ladies and gentlemen, it's good to inform you that this lecture is being streamed live on YouTube, and I'll be sharing the link with you as soon as we can. Now, what is a computer? You do understand that the computer does a lot of things, and majorly, I don't think it is appropriate to start looking for a singular definition that defines what a computer is. But you know, in the framework of a computer, we are talking about a device that can take in some set of inputs and transform those inputs via the concept of processing to a usable output. Of course, this would not be possible without some components that comes together to form the computer. The first one is the CPU. The CPU is an abbreviation that stands for the Central Processing Unit, which, like the name is stretched, processing unit, processes all the components of instructions that come into the system. Then you have the main memory. Of course, you know what the main memory is. And there goes the secondary memory. We have input devices and we have output devices. Example of the input devices are your keyboards, are your microphones, and many other devices. And while examples of your output devices are your display monitors and tapes. Now, we'll now take it one after the other. We'll look at all of this concept. I have seen some hands being raised up. I mentioned to you that if you have any question or any you want to inform of any development, please use the chat box. We cannot allow people to be talking while this class is going on. So the central processing unit is better said as the heart of the computer. It is the heart of the computer. But what do we mean by that? Or you can even call it the brain. It is at that point where you have the computer think of processes, thinks of instructions and how to implement them. It is the think tank, the logical framework of the computer system. Imagine what your heart does. So look at the way your brain functions. That is the same operational framework that is being done by your CPU. The CPU, again, is the central processing unit. But this central processing unit, just like the brain or the heart, also contains other parts, or these parts are also major parts. Of course, there are three fundamental parts of the CPU. The first one is the control unit. And what it does is simply the coordination of all the activities that exist within the computer. Imagine something coordinating all the activities of a system. That is the control unit. The arithmetic logic unit performs calculations. You will recall that the ALU has always been mentioned time over time when you get to the area of trying to provide one arithmetic expression and its generation. You find out that computer devices are the best framework and devices to help do calculations in the current time. I'm happy to inform you that the computer devices are not just an expert system, but computers are existing because man, me and you, can think of operations that are to be performed by the computer. So what does this tell us? It tells us that a computer cannot do anything that we cannot do. But the computer has the capabilities to do those things that we will do faster and with high level of accuracy because of the discreteness that is embedded in the computer and because of the fuzziness and the ambiguity that is embedded in man. So our arithmetic logic unit, the ALU, performs all the calculations that exist within the computer framework. Then the registers. What is it? It's just like a storage as well, but it stores a small amount of data and instructions. So at a time, once at a time, it stores the data and the instructions. We have the main memory. And of course, this should not be a new terminology to you. I can remember that a lot of you are joining this. I can note, not remember, I can note that a lot of you are joining this lecture session with a mobile device. And I do understand that at the time you were procuring this mobile device, you asked for the functionalities and the specifications of this device. You will say, what is the RAM? What is the RAM? What is the ROM? You want to know the size. You want to know how fast it can process an item. The RAM is also a memory that is bigger than the register, but smaller than the hard drive. And what it does is that it temporarily stores a program that is being run by the computer and also allow the data required by the computer to be temporarily stored. And that's why I told you in the earlier session, in the earlier slide, that you can store your program and your data temporarily in the register. So this is a concept of a memory framework that is a bit bigger than the register, but smaller than the hard disk. It is volatile. What do we mean by that? When it is shut down, when there's no power in it, the RAM will not store the data. All the data in the RAM is lost if there is an interruption in terms of power. So it means that if you are working on your RAM and there is a sudden power outage, it means that your data at that point will be lost. But the secondary memory is non-volatile and is a permanent storage. You put a flash drive in your pocket, you store your data, you take it from one point to the other. If power got shut down, you still take your flash drive and you move away from it. Your USB flash drives, your hard disk are examples of the permanent storage. Of course, the sizes are larger than that of the RAM. However, if you want to access the hard drive, it will take you a longer time. That is like 5 to 10 times higher than the time it takes you to access your RAM. So you can now see the advantages and the disadvantages of each of these storage framework. Now, these storage frameworks comes in a way that they complement the functionalities of each other. So it will not be appropriate to say, why am I using a RAM and not using a ROM? All of them work together. One is helping you to temporarily store some data and register for processing. The other one is helping you to store the output of that processed resource. So that is a whole mechanism of how the system works. Now, our interest in this course is computer language, because we are going to talk about programming language. But before like I told you earlier, I am speaking a language to you called English. We want to understand the computer language. Which language does the computer understand? Computer, do they speak? Will you tell me that your computer can speak? If it can speak, what language will it speak? Those are the things we are going to look into. Like I always tell you, that the computer is an entity like human in its own framework, because it has the capability to do everything that we are doing. It can speak a language of its own. And that is why we say each computer has its own machine language. This machine language is called the assembly language. And ladies and gentlemen, I am expecting that at this point to be taking notes. And this assembly language is used to execute the very, very, very basic operations. Operations which include how to load, to store a data, to retrieve data from the memory, to copy data into memory, even to perform some arithmetic operations, including addition, subtraction, multiplication, and division. But there's a problem with machine language. The problem is that it is very, very difficult to write by human, and it's also very difficult to understand. So when you talk about a machine language, you see that is a language that is at the level of that machine. So because of the difficulties that are existing in machine language, it is important. I can inform you, and I'm glad to inform you, there are 239 participants in this class, 240 now, and that's a great one. And I thank you for sharing this time. And be assured, we are going to be taking it easy as it is, and I will be, I think my focus will be that every one of us do understand the concept of what we are learning. Now, as being said, because of the difficulties that are existing, in understanding the low-level languages, which you call the machine language or the assembly language, then computer scientists has defined the problem and has been able to come out with a framework called the high-level language that are easy to program and use, because the low-level language are difficult. They are machine language. Where an ion is talking to an ion, it is difficult for a woman to be between these ions. However, we have seen this problem, and we have come to the design board to say, how do we now help our computational process? The only way to help our computational process is by developing a language that can be a secondary language to that assembly language, which is a low-level language. Yes. So the program now is called the high-level language. But these high-level languages are written in just the way we are speaking. They are written in something that can be read and can be understood in an English-like manner. However, they will need compilers and linkers to convert whatever we have written in a language that is similar to what I'm speaking to the language that the machine will understand. So examples of high-level languages are Fortran, C, C++, Java, Clojure, Pascal, Scala, ML, many of them. And at the latest count, there are more than 700 programming languages. Because all you have to do is sit down together, understand the framework of your language, and develop a structural representation of that language. But let us look at the benefit of this high-level language. With emphasis on Fortran, which is the subject of concern in this class. One of them is that the program can be compiled on any machine that has a Fortran compiler. It means that for you to translate a Fortran language to an assembly language, you must have what we call a compiler that can compile a Fortran program. I'll take that again. For you to translate or convert a high-level language with emphasis, especially, for example, Fortran, to a low-level language, which is a machine language, understood by the machine, what you have to do is to get a compiler for that high-level language. So it means that if you are converting Fortran, you will need a Fortran compiler. If you are converting C, you will need a C compiler. If you are converting C++, you need a C++ compiler. Whichever language you are compiling, you will need a corresponding compiler. Now, when you talk about computer systems, their operations and the programming framework, you cannot do anything without being sure of how data is being represented in the computer. So one important concept is the data representation in a computer. Data is represented by millions of switches. And each of these switches can either be on or off. I enjoy all of you to please put down your hands. If you have any question, please use the chat box. Put down your hands, please. So data can be represented by millions of switches. And when you say a switch, it means at a time it can be on, at another time it can be off. So we are saying that when you have your data represented within your computer framework, it is either represented as an item that is on or an item that is off. If it is on, we say it is represented as 1. If it is off, we say it is represented as what? 0. So 0 and 1 are the two binary digits, and that is why we call them bits. Bit is actually generated from binary and digits. Binary and digit bits. So we use a combination of zeros and ones to represent other numbers and characters as well. That we are now telling you how the data, if you write, my name is Toyin Enikuomehin, if you write that on in your program, it is being translated to series of zeros and ones. And that's why we say that those combinations of zeros and ones are used to represent other numbers, not just numbers, and characters as well. The smallest common combination of the bits, zeros and ones, is called a byte. A byte is the smallest common combination of bits. And a byte is a group of 8 bits. A byte is a group of 8 bits. Please note, a bit is made up of 0 and 1. The smallest common combination of bits of zeros and 1 is a byte. So when you leave the category of bits, you go to the category of bytes. But what are the bytes? What do you call a byte? A byte is a group of 8 bits. So you have a bit that has 0 and 1, 2 binary digits. Then they form a byte, which is 8 bits. Then you have a bit. When you have 2, 4, or 8 bytes, we come together to form a word. A word is a group of 2, 4, or 8 bytes. Generally, most PCs is an abbreviation for personal computers, have 4 bytes. They are 4-byte words. Because a word can be 8-byte word, can be 4-byte word, can be 2-byte word. But most PCs are 4-byte word. Of course, because we've been talking about zeros and 1, it takes us to some of those things we learned in the secondary schools. And I'm sure you can remember those days when you were in schools and they were telling you about the binary number system. I'm so glad that I do know that you are so happy to hear again that today you'll be learning something about those things you have learned in the past with emphasis on the binary number system. The number system used by human is the decimal system. Our number system is the number that we use in base 10. So if you say somebody gave you 1,000 naira, that 1,000 naira you are writing 1,000 as a number in base 10. And when you talk about base 10, it means that there are 10 digits because it's a system. The 10 digits starts from 0 to 9. Please note, it is not 1 to 10. It is 0 to 9. Each digit in the number represents a power of 10. Now, I'll give you an example here. The number 221 is 2 asterisk 10 raised to power 2 plus 2 asterisk 10 raised to power 1 plus 1 asterisk 10. So if you look at 2, and you can see my cursor, this is 221. If you look at 2 here, this is the 2. We say each number in each digit in a number, this is a digit in this number. This is a digit in the number 221. Each digit in a number represents a power of 10. So this is 2 times this is the power of 10. 10 raised to power 2. This is 2 times 10 raised to power 1 because you are coming from 2, 1, 0. You remember the way we number it, that this will be raised to power 0, this will be raised to power 1, and this one will be raised to power 2 because we are talking about 0 to 9. Where 10 raised to power I is 10 raised to the exponent of I, which can be 0, 1, 2, 3 to whatever it is. Now, similarly, we can convert a number from binary, which is base 2, to base 10. And ladies and gentlemen, it is my pleasure to also inform you that at this point, I'll be taking down some assignments. And this is going to be an assignment for you. You are going to visit the LASU assignment management system. It's an assignment portal. Your assignment will be set tomorrow, and you will have 2 days to a day. Yeah, okay. You will have 2 days to attempt the assignment and submit at the deadline. But the assignment is framework that you have to go and enroll yourself for an assignment for this course. Once you enroll yourself, I'm going to be sharing the link for that portal with your HOCs. You enroll yourself. Each time an assignment is posted, you will receive an alert automatically. And you'll be given 48 to 72 hours to complete the assignment and to submit the assignment. In some specific situations, especially in scenario-based tests and assignments, plagiarism detector will be activated so that if you copy your colleague, the system automatically informs us of what you have done, and we shall be able to take appropriate steps as necessary. So coming back to where we are. So we look at the number 101. So you have 1 asterisk 2 raised to power 2, just in that order. 0, the first one is raised to power 0, 1, 2, and you can have this to be 5. So if any bits are available, then those bits can be represented, can represent the 2 raised to power n possible values. Of course, we do know that 1 byte is 8 bits, and that represents 256 possible values. 1 byte is 8 bits. So if that means that you can take 2 raised to power 8, 1 byte is 8 bits, and that represents 256 possible values. Of course, what we have to do here is to say 2 here raised to power 8, because we are talking about 1 byte. So 1 byte, you can get this is how we got this one. 1 byte is 2 raised to power n, and n here is 8. So 2 raised to power 8 will be 2 times 2, 4, times 2 times 2, 16, times 2 times 2 times 2 times 2 times 2, which is 8, is going to give you 256 possible values. So 2 bytes will be n raised to power 16 bits, and that can give you 65,536 possible values, which is the total number of rows in Excel 2003 version. So this is one of the assignments I'm going to ponder on with an immediate answer. So we'll be giving you expressions like this to ponder with, and you can look at this video on and on again. You can go back to it as a guide into, because the essence of teaching you is to know. And that's why we are making this lecture very public, so that you can revisit the site time over time and get to drive the content that is required from it. So which of the following ranges will best describe the possible value of a byte? 0 to 255, 1 to 256, minus 127 to 128, minus 128 to 127. So which one is the answer that will represent the possible values of a byte? Of course, you agree with me that the answer is 4, because a computer must store both negative and positive integers. And the following example will illustrate how this can be achieved. So, you know what you call a car odometer? If you look at your car, the cars in your house, you can get out to the car park tonight, get a torchlight, or put on the light and look at your odometer. You see car odometer or the millimeter. Of course, the content is not a content that is in the book that will be used anywhere. The content is a content that you can verify. But this is the type of readings you have. And it gives you an initial value, then the values after 2 miles, then the value after reversing some of the forms. So it gives you the values as you use the platform. The platform is as the odometer readings continues to update itself. So as you use the car, as you move from one point to the other, the readings changes, and these readings are recorded, and the cumulative value is generated. Now, let us look at the storage of these 8 digits integer in base 10 system. So what do you have? You have a representation of 50 million, you have a representation of minus 49 million, a representation of minus 1, and so you must be able to develop a system. And that is the thought of the framework for the understanding of the binary system that can accommodate both positive and negative integer as data that can be represented with the computer framework. And all of these are the expressions of a 4-bit integer. So, as a randomness to this, before getting to the appropriate table, we will now conclude by saying for today that 2 other number systems that are also useful are the octal and the hexadecimal. That is the ones of base 8 and base 16 respectively. And the conversions will show the transformation of numbers from one of these system to the other system. We'll be looking at that at a later time, but today we will end this class here. We'll take questions so that you can have enough time to assimilate, ponder, and revisit what you have been taught today, so that you can have a proper framework and understanding of this class. We have done so well today. The participation is good enough. And I'm proud that we are ending this as at where we call the types of data. So we'll be coming back to look at the types of data, and we'll be calling it a full lecture that will involve practical sessions where after looking at the types of data, because we'll put them to practice. Ladies and gentlemen, I thank you for listening, and it's my pleasure to just be with you. So at this point,